Hello everyone, my name is Kishalay Das. I am a PhD student at Indian Institute of Technology, Kharagpur, India. Here I am going to present our work, CrysGNN, Distilling Pretrained Knowledge to Enhance Property Prediction for Crystalline Material. In this work, we have developed a Pretrained GNN model, CrysGNN, which improves the performance of downstream property prediction tasks for crystalline material. This is a joint work with Dr. V. Samanto, Dr. Pavan Goel, Dr. Lee, Dr. Satyajit Bhattacharya and Dr. Niloy Ganguly. So without further ado, let's begin. So first I'll give you a brief background about crystalline material. A crystalline material typically looks like a 3D periodic structure where we have a minimum unit cell where different atoms will have some position in the 3D space. And this will get repeated infinite times on a regular lattice. For example, here we have NaCl material which have this unit cell structure where we have one Na atom and one Cl atom. And this basic structure will get repeated in three directions to form this crystalline structure which is periodic in nature. Along with this crystalline material, they have different properties like magnetic structure, electronic structure, thermodynamic stability, etc., which signify the physical feature of the material. Now, given a crystal material's 3D structure, predicting these different properties is a challenging and important task in material science because it helps to discover new possible materials with the desired properties. Historically, density functional theory or DFT has been an effective tool to estimate these materials' properties, but one of the major issues with DFT is it's computationally expensive, hence it eventually makes the screening process of new material inefficient. In recent times, data-driven approaches emerged as an effective tool for predicting different crystal properties which are as accurate as DFT, however, much faster than it. The majority of the existing state-of-the-art models represent material by a graph structure where they establish edges only between the nearby atoms and use a deep graph neural network to learn crystal structure representation. Now, architectural innovation of these SOTA approaches towards accurate property prediction comes from incorporating some specific domain knowledge into a deep encoding module. For example, GNN-based approaches like CGCNN, GAD-GNN, MAGNET construct a multi-edge graph by establishing edges only between nearby atoms within a pre-specified distance threshold that is typically 8 angstrom. Recent models like ALI-GNN incorporates bond angular information into their encoding module to capture many-body interaction between atoms and improves property prediction accuracy for a large range of properties. Moreover, data scarcity across properties is a known issue in the material science, which makes these models difficult to train for all the properties. Recent models like CrysHPP or LMNet adopt the concept of transfer learning to mitigate the data sparsity issue across different properties. But different crystal properties are a very complex function of the crystal structure. That's why it's not always easy to incorporate specific domain knowledge about a specific property into the deep encoding module to improve the performance of the model. That's why we come to our problem statement for this work, that can we leverage a large amount of untapped crystal material structure to pre-train a deep GNN model which can learn these complex hidden features which otherwise are difficult to identify. There have been quite a few works recently on pretraining GNN, and one of the pioneering work in this direction is by Hu et al., where authors propose node level and graph level pretraining on GNN. Where through node level pretraining, they try to capture domain-specific knowledge about nodes and edges. On the other hand, through graph level pretraining, they capture global graph level knowledge. But these prior works, they mostly focus on chemical and biological datasets, which are difficult to extend directly to the crystalline material. Because firstly, the structural similarities are very different between molecules and materials. Secondly, for graph level pretraining, they use supervised property prediction task using a huge amount of label datasets from chemistry and biology, which makes it less effective in material science community where property level data is extremely scarce. Finally, they follow conventional pre-trained fine-tuning framework, which limits the knowledge transfer capability of the pre-trained model if downstream tasks are very different and downstream datasets are very different. Hence, we developed a pre-trained GNN model, CrysGNN, for crystalline material, which captures both local or node-level chemical semantics and global or graph-level structural semantics of crystalline material. We curate a new large untapped crystal dataset with 800K crystal graphs to pre-train CrysGNN model. We have introduced a self-supervised graph pre-training method which captures connectivity of different atoms, different atom properties, and graph similarity from a large set of unlabelled crystal graph data. Subsequently, we distill important structural and chemical information of a crystal from the pre-trained CrysGNN model and pass it to the property predictor. Finally, we retrofit the pre-trained CrysGNN model into any existing state-of-the-art property predictor to improve their property prediction performance. Now, before going into the actual model, I'll first explain how crystal material can be represented as a multigraph. For every given node or atom, we consider an 8 angstrom radius sphere around it, and all the other atoms that is coming within that 8 angstrom radius sphere, we connect the edges between those atoms. For example, in the image, if you consider the pink atom and let's have a 8 angstrom radius sphere around it, you can see one green atom, 3 yellow atoms and 2 blue atoms are coming within the sphere. Hence, in the multigraph, we have one edge between the pink and green node, 3 edges between the pink and yellow node, and 2 edges between the pink and blue node. For any given node, XU denotes the node feature set. Then for any pair of nodes, we have k different edges with different edge weights corresponding to bond length or distance between the node pairs. And these are the different chemical properties which forms the feature set, like electronegativity, group number, period number, valence electron, covalent radius, etc. Now I will explain how CrysGNN will be pre-trained on node level. For that, we propose two self-supervised learning methods. Given the multigraph structure of the material, we will pass it through a CrysGNN encoder, which is basically few layer of GNNs applied on the multigraph structure of the material to generate the node embedding through message passing and neighborhood aggregation. Then given the set of node embeddings, we pass them through a decoder to reconstruct two things. First of all, node features, and secondly, node connectivity. In crystalline material, node features corresponding to different chemical properties associated with the constituent atoms. And through reconstructing this feature, CrysGNN captures local chemical semantics around the atom. Then, through reconstructing the local connectivity around the atom, CrysGNN encodes the periodicity of the node, that is the number of neighbors around it, along with the relative position of the neighbors and the bond length. Further, we propose graph level pretraining, where our goal is to capture structural similarities between crystal graphs. For that, we leverage two inherent properties of crystalline material, space group number and crystal system. Space group describes the symmetry of unit cell structure in 3D space. There are total 230 unique space group numbers, and every crystal has a unique space group based on its unit cell symmetry. And based on the space group number assigned to a crystal material, we can categorize them into 7 broad categories of crystal system. And here are the example of those crystal systems like cubic, hexagonal, tetragonal, etc. Hence, we adopt supervised and contrastive learning to learn structural similarities between graph structures using the space group and crystal system information of the materials respectively. Here is the graph level pretraining that we have followed. We fed the graph structure again into CrysGNN encoder, which give us node embeddings as output. Given the set of node embeddings, we use a symmetry aggregation function to generate graph embedding. Then we first pass this graph embedding through a multilayer perceptron to predict the space group number. Further, given a set of crystal graphs, we use contrastive learning framework which maximizes the similarity between crystals coming from same crystal system and minimize the similarity between the crystals which is coming from different crystal system. For example, here G1 and G2 both coming from cubic crystal system, and on the other hand G3, G4, G5 they are coming from different crystal system. So through contrastive loss, CrysGNN will maximize the similarity between the positive pair, that is G1, G2, and minimize the similarity between negative pair, that is G2, G3, G2, G4 and G2, G5 in the embedding space. Once the CrysGNN is pre-trained, we aim to retrofit this model into any SOTA property predictor to enhance its learning process and improve the performance. Now we have this SOTA property predictor which can be any state-of-the-art existing model which takes this crystal graph structure as input and generate node and graph embedding from the material, which are further passed through a multilayer perceptron to predict different crystal properties. This is a simple supervised regression model where we compute mean square error loss between the actual value of the property and the predicted value. Now we have this pre-trained CrysGNN encoder which takes the same crystal graph structure as input and generate node embedding. Now we distill information from CrysGNN to the SOTA property predictor using this additional knowledge distillation loss, where we try to minimize L2 loss between two sets of node embedding. And our final loss is delta times the actual supervised loss of the SOTA property predictor and 1 minus delta times the knowledge distillation loss. And this distilled information from the CrysGNN helps to improve the performance of SOTA property predictor. And one of the advantages of using distilling knowledge from the pre-trained model is we can retrofit the pre-trained model to any downstream property predictor irrespective of their architectural design. Now before getting into the part of experimental result, I will first discuss the datasets that we have used for both pre-training and property prediction tasks. For pre-training CrysGNN, we have curated around 800k crystal materials from two popular material databases, that is OQMD and Materials Project. From OQMD, we have collected around 670k crystals, and from materials project, we have collected around 130k crystals. And please note, these data are property untagged. We only have the graph structural information for this crystalline material. For evaluating different state-of-the-art models for their property prediction accuracy, we have used two benchmark DFT datasets which have been used by previous model. First of all, MP 2018, which is a subset version of materials project database, which contains 69 cake materials with two properties, bandgap and formation energy. Next is Jarvis DFT datasets, which consist 55k materials with 19 different properties. Also, to investigate how pretrained knowledge helps to mitigate DFT bias error in different state-of-the-art property prediction model, we also take a small dataset OQMD EXP containing 1500 available experimental data of formation energy. Now I will explain the experimental results and evaluate the performance of different state-of-the-art models on downstream property prediction tasks in this table. We choose four diverse state-of-the-art algorithms for crystal property prediction, that is CGCNN, GATT-GNN, CrysXPP and ALI-GNN. For any SOTA model, the results of the left column are for the original SOTA model reported by the respective paper, and the results of the right column are the distilled version of the model, where we have trained the model with distilled knowledge from CrysGNN. Top rows of the table are for the properties of materials project dataset, and the bottom rows are for the properties from the Jarvis dataset. Here, for each property, we have trained all the model for 80% data, validated on 10% data, and tested on rest 10% of the data. And we report mean absolute error or ME of the predicted and actual value of the particular property to compare the performance of different participating methods. We observe that the distilled version of any state-of-the-art model outperforms the vanilla model across all the properties. We also observe average relative improvement across all properties for models like ALI-GNN and GATT-GNN is lesser compared to other models like CGCNN and CrysXPP. A possible reason could be that ALI-GNN and GATT-GNN are much more complex model with more number of parameters than the pre-trained CrysGNN framework. Hence, designing a deeper and much more complex GNN encoder for CrysGNN may help to improve further. This requires further investigation and we keep it as a scope of future work. Further, to demonstrate the effectiveness of the knowledge distillation method compared to conventional pre-trained fine-tuning approaches, we compare our method with existing pre-trained fine-tuned model. For this experiment, we take fine-tuned version of CrysGNN and compare it with CGCNN distilled, CrysXPP and pre-trained GNN, which is proposed by Hu et al. We consider these three models, that is CGCNN distilled, CrysGNN fine-tuned and CrysXPP, because their encoding architecture is same, where they have used simple GNN. We pre-train all the baseline model on our curated 800k crystal dataset and fine-tune them on 7 properties in Jarvis DFT dataset and report the MAE in the following table. We observe that distilled CGCNN outperforms fine-tuned version of CrysGNN and both the baselines with significant margin for all the properties. Pre-trained GNN by Hu et al. Perform the worst, and the potential reason is that this model is designed considering simple two-dimensional structure of molecules with a minimal set of node and bond features, which is hard to generalize for crystalline material which have very complex structure with a rich set of node and edge features. Finally, one of the fundamental issues in material science is that experimental data for the crystal properties are very rare. Hence, existing SOTA model has to rely on DFT calculated data to train their parameter. Hence, DFT error bias is prevalent in all of the SOTA models. Few of the recent studies has shown that pre-training helps to remove this error bias from the SOTA models when fine-tuned with experimental data. Hence, we investigate whether SOTA model can remove their DFT error with distilled knowledge from the pre-trained model using a small amount of available experimental data. We use OQMD EXP dataset to conduct an experiment where we train the SOTA model on 3 different experimental setups. First, we train the model on fully DFT data and test on the experimental data. Then we put 20% of the experiment data into the training set, and finally we put 80% of the experiment data into the training set. And we observe with more amount of experimental training data, all SOTA models are minimizing the error consistently. In conclusion, I will say in this work, we present a novel but simple pre-trained GNN model, that is CrysGNN for crystalline material, which captures both local chemical and global structural semantic of crystal graphs using node and graph level pre-training respectively. We have curated a new large untapped crystal dataset with 800k crystal graphs to pretrain CrysGNN, and we have already released the pretrained model along with the last dataset for the community in the following GitHub repo. We distill important knowledge from CrysGNN and inject it into different state-of-the-art property predictor to enhance their performance. We believe this approach of distilling knowledge from pretrained model can have applications in other domains also. Extensive experiments show that it has superiority over conventional fine-tuning model and its inherent ability to remove DFT-induced bias. With this, I end my presentation. Thank you all for listening, and if you have any question, you can ask me.